paper is about expected returns and the large language models. Probably yesterday you have heard about how great ChatGPT is. But this paper is a bit more broad than ChatGPT. We're not motivated by it. We have started work on it when Google released its BERT model, which is one of the first large language models. The reason we're interested in text mining is that economic text is constantly generated by human writers like us and reporters, striving to understand and make predictions about economic phenomena. Right, so maybe we provide a bit more interesting information or useful information than just pure numbers. Now, the finance and accounting literature have begun to extract information from certain text sources, such as financial news press, regulatory filings, and social media. But this research agenda of improving economic models through text mining remains its earliest stages. Right, so first of all, it has mainly focused on the rather small market-relevant text data. Typically a single specialized data source, one at a time. In addition, for each data source, the representation is often very rudimentary. Okay, so what is prevalent in the current literature is that we use naive sentiment scores or bag of words approach to represent an article. Now, why there is a limited use of text data to date? Well, the main reason is there is a lack of regular structure, right? So language is an extremely nuanced information encoding scheme. As a result, you need highly complex models to truly understand, to truly unearth information contained in text. Now, this poses two challenges, right? So number one is, this is a technological barrier to entry, and that would exclude researchers who lack the specialized skill set necessary to operate such models. On the other hand, the high computational cost of such models exclude researchers who might have the skill set but not able to, get enough funding to actually work on such complex models. So the bottom line is text mining is still an underexploited data source for understanding answer terms. All right, so what are the large language models? So they're also called foundational models of language. So this is an emerging paradigm of AI that was first developed and then popularized in the field of NLP. So the key idea of a large language model is that there is a specialized research team to perform what we call a Herculean feat of estimating a general purpose language model. Oh, really? Okay, sorry. Is there a microphone or something?
Yeah, in the drawer.
In the drawer? Oh, yeah. This one?
Yeah,
does this work? Sorry. All right. So the idea is for such a research team, typically a very rich startup or Google, Microsoft, to actually fit such a complicated model with a huge number of parameters on truly big data set. Okay, so and such data set typically span many sources and things. And for each large language model, this fit is performed just once, and then the ST model is made available to downstream tasks, such as researchers like us, to essentially study how we use such language models in downstream tasks. And most of these tasks so far are within the domain of NLP. Now, where are these benefits? Where are the benefits of large language models come from? Well, it mainly comes from this sophisticated and well-trained text embeddings. Right? And such text embeddings are much richer than naive embeddings like bag of words, which completely ignore all information on syntax and semantics. But large language models can easily capture those things. The benefit also comes from the expressivity of massive nonlinear model parameterizations and also the very rich training data set across many domains. If you think about this, perhaps this is the first time we can use this so-called unprecedented scale of knowledge accumulated through human history to really kind of dive into finance research. So we were very excited about it, right? So we started looking at these problems after BERT, which was first released around October 2018. And then there is a better version of BERT Roberta. And then, this list goes on and on. And as a result, our papers still have not finished because we're trying to always use the most advanced technology. At some point, GPT 3.5 or ChatGPT shows up, but they're not open sourced, okay, even though the company is OpenAI. So we use OPT instead, which is an open source implementation of GPT 3.5. And later on, there is a Llama and Llama 2. So we're currently experimenting with these models. So Llama 2 is claimed to have comparable performance relative to ChatGPT. So we're also very excited about it. Now, in terms of number of parameters, as you can see, number of parameters is really huge, very different from the usual kind of econometric models that we have been working with in the past, right? So we have like 7 billion, 13 billion, etc. All right, so what is the objective of today's talk? So we're really trying to construct, refine news text representations, or so-called embeddings, right? So derived from large language models. So very recently, Rob and Xavier has a paper, has something posted on SSRN to kind of talk about asset embedding. So we are kind of doing embeddings from some other database. So we're looking at large language model to run embeddings. And our main research contribution is to demonstrate the benefits of large language models relative to the existing approach, and so to compare their performance, right? Basically. All right. So this paper we want to use the simplest methodology ever. Okay, so something that everyone can easily replicate. You'll get a deterministic answer instead of any randomness, like in the random forest or things like that. So the answer will be deterministic and very simple. That said, what we can only provide to is a lower bound of how great large language models are, right? So you can certainly improve on these results. Now we're going to look at two exercises. Number one is sentiment analysis, right? So the idea of sentiment analysis is simply to use some X variables derived for stock I times T, okay, or article I times T, to actually predict the label of this article, whether it's a positive or negative. So I stands for a news, and T is the publication time. Because our data set has a one-to-one correspondence between news and the stock, so there's no difference between news and stock. Now, for classification problem, because YIT is a 0-1 variable, right? So 1 means positive, 0 means negative. So we're going to use the simplest logistic regression framework. XIT is going to be embedding for article I times T, which is a vector representation of an article. That is something we're going to talk about in a minute. All right. So typically getting a good YIT is hard. You need to hire a bunch of experts to study article and then give us labels. So here we use a very cheap way of generating sort of objective but noisy labels. Whether this is a good approach or not really depends on the empirical results I'm going to show you. So we're using the 3-day return.
Very clarify.
Yeah.
What do you mean by embedding?
Embedding means a vector representation of an article. So like a long vector. So vectors are something computers can understand. Text is not, right? So now the second exercise we're looking at is return prediction, right? We directly regress returns of the next period, IT plus 1, onto this period embeddings, XIT, using the panel linear regression setup. Now, obviously, you can do something much fancier than this. All right, so before I'm going to talk about XIT, I'm going to tell you that XIT is high dimensional, so we have to use some regularization, and the approach that we use is ridge regression. Okay, so again, very simple. All right, so now let's talk about XIT. So where can we construct XIT? So we're going to compare lots of different approaches, starting from the bag of words. Bag of words can provide an embedding of an article, but it's a very inefficient embedding. It's a 0-1, it's a one-hot coding, meaning that you're going to represent an article simply using the words frequency. Words showing up in this article has you can count how many times it shows up, and you're going to represent an article using a long vector. And typically there's 30,000 words in the dictionary. That's why bag of words representation is typically 30,000 by one vector, right? So very large with lots of zeros. Now to efficiently use this approach, we use an earlier paper of ours that make use of bag of words representations. Now the second approach is more advanced. Some of you have been working with that as well, called word embeddings, right? the key idea of word embedding is that the meaning of a word is given by the company it keeps. So this is a very interesting hypothesis in linguistics. What is the main contribution of this hypothesis is that it translates a linguistic problem of figuring out the meaning of a word into a statistical problem of finding out which words are more closely related to a word, right? So therefore, we can use statistics to come up with the embedding for a word. Once you have embeddings for each word, you can simply take an average to obtain the embedding for an article, right? By looking at all the words this article used and take an average. So that's how we achieve a document or an article embedding from word embeddings. Okay, so to be clear, the word embeddings, each word embedding is a constant vector, does not change with context, right? So, and then you just collect all the words in an article and take an average. All right, so finally is the large language models, okay? So the way we use large language models is, again, extremely simple, okay? So once we have these large language models downloaded from Hugging Face, which is where some of these open source large language models are, and then you kind of put your articles into it, okay, pass your articles into it. And then you achieve embedding for each token of an article. So token here is the minimal unit of an article, typically a word, but we do it more carefully, we call it subword. So microeconomics, for example, is going to decompose to macroeconomic and S, so 3 tokens. So in the end, you obtain a token representation, a vector representation for each token of all words in these articles, right? So then you take an average. All right, so that's something that we do, which is again extremely simple. Not necessarily the best way of doing it, but it's one way of doing it. So essentially we translate token embeddings into an article embedding. So now these different large language models, they can take up, some of them can take up to 500,000 tokens like BERT and produce a 1,000 dimensional vector. All right. And OPT, which is the most advanced model we consider so far in this paper, can handle as many as 1,000 tokens. So later on, I'm going to show you some summary statistics of how many tokens we're using for each article. Where are these? For some articles that have very long, we definitely have to truncate it to use the first 1,000 tokens to build such embeddings. All right, so why not ChatGPT? Well, we believe ChatGPT is can be deployed as a sentiment analyzer, but we also believe that its primary function as a chatbot indicates that it is perhaps not the best way designed for forecasting. So there are several reasons, right? So first of all, the sentiment score generated by ChatGPT might not be cross-sectionally comparable, right? Unless you give ChatGPT lots of articles at the same time and ask about what are the relative scores. Otherwise, you cannot imagine it giving you an accurate comparison. And the secondly, it's not really practical for trading purposes. The API is not easy to use. And finally, it does not provide you with any measurement of expected returns, which is something that we are interested in. Okay, so all right. So now in terms of how much time do I have? Oh, okay, sorry. Okay. So now in terms of data, we're looking at international stock returns data set. And in terms of news, we're looking at 16 different countries' news, written in 13 different languages. Okay, large language models can easily handle different languages as well. And there are 2 types of news stacks in US. Some of them are articles. Some of them are alerts. Alerts are only headlines, and they're typically for emerging events and developing news. So what's cool about this data set is for alerts, they come with something called take sequence. All right, they tell you exactly which wave of alerts it belongs to, right? This is the first wave of alerts or second wave of alerts. So we're going to make use of that label to make some points. All right, so this is a summary statistics. In the event after cleaning, we have about 3 million articles and alerts left. 3 million articles and 3 million alerts for US data and a bunch of other countries as well. So on the bottom, we have some countries with very few data set of news. So we cannot build portfolios to understand the performance. So we include them, simply trying to see, the different languages can also work, All right, so instead of showing you with boring statistics, I'm just going to show you the portfolio performance. All right, so once we have made predictions about future sentiment or future stock returns, we can do a sorting, long top 20%, short bottom 20%, do a long short portfolio, hold it day by day, and kind of calculate the Sharpe ratios. So that would translate all the statistical correlations and accuracy into portfolio performance. So now OPT, which is our most advanced model, achieved a Sharpe ratio of 4.51. And of course, value weighted is much worse than equal weight. That's not surprising. That being said, all of these companies are mentioned in the news. There's about 1,000 companies mentioned in the news per day. So most of these companies are large, right? Smaller, very tiny companies. They don't have news. So Roberta is a better version of BERT, and indeed, Sharpe ratio 4.10 is higher than 3.65 by BERT. And word-to-back is word-based approach, and it achieves a lower Sharpe ratio, 3.13. Okay, so you can ignore FinBERT, something that I have no time to talk about. And system is our approach, achieve a reasonably good approach, reasonably good Sharpe ratio, very close to BERT. Now, this is a cumulative return of long-short OPT portfolios. The black line is long minus short, blue line is long, and the red one is short. The lower the better. So the yellow line is market. So apparently, it works reasonably well. All right. So here we can show you the performance of return prediction portfolios, right? So the previous ones are sentiment-based, and this is return prediction-based. So you can do long-short portfolios based on expected returns. Now 4.84 is the OPT. All right. So essentially beyond just the sentiment score, it seems like the embeddings can actually contain more information than just positive or negative. All right. So this is something that we find a bit more interesting. Right, so these numbers on the first column are the article Sharpe ratios that I show you. Now here on the second column, I'm showing you the Sharpe ratio you can get by just trading alerts. Okay, completely ignore articles, only trade on alerts. You can see a substantially higher Sharpe ratio. So what if I just trade the first take sequence of alerts, the first wave of alerts? You get a very high Sharpe ratio. Now the second wave of alerts is much lower. Okay, it's much lower. So, if I were you, if I were a hedge fund manager, I would invest more money trying to be fast rather than trying to kind of get the most advanced model, because OPT 3.60 trading with tick sequence 2 does not achieve as high a Sharpe ratio 4.62 by a bag of words approach traded on tick sequence 1. So in financial markets, speed matters far more than the complexity of the model. Now, on the bottom, you have the median token size for each article, and you can see, if you can handle 512 tokens, you basically cover 50% of articles without any truncation. So truncation will have no effect, as we will show you later on. All right, so some of you wonder where these news come from. Are these all learning news? The answer is no. Okay, if we just exclude all the learning related news, and you can still achieve a Sharpe ratio of 4.10. And you can also look at different ways of portfolio formation. You can try different labels. Instead of using raw returns, you can use factor model residuals to form label, and you still get pretty good, even better Sharpe ratio, right? So if you use CAPM in industry as control to get residuals and use sign of the residual to label your article, you get 5.66 Sharpe ratio, which is even higher than the results that we had before. Now, in this slide, I'm trying to understand the impact of truncation. So again, we have corresponding regression results in the paper, but I find it boring, so I just show you portfolio results directly. Okay, so here we're looking at two models, OPT and the OPT truncated with 1,000 tokens. So OPT can handle 512 tokens, right? Everything is based on 512 tokens. And here we look at what if we handle more tokens, 1,000, double the token size. And as you can see, the Sharpe ratio is pretty much the same. There's not much difference. All right, so essentially what this tells us is that, if you try to embed an article, a news article, the first 512 tokens basically captures all the information the reporter tries to convey. All right, so what would happen if we take into account transaction cost? I don't have much time. You get a positive Sharpe ratio if you trade alerts. So probably not as good as 5 point something, but get like 1.6 something. Here we're kind of looking at the virtual complexity, right? So we can obviously use, because there are many versions of OPT from only 100 million parameters to 6.7 billion parameters. So you can see that there is not much difference in terms of Sharpe ratios from low to from less complicated models to more complicated models. So sometimes less complicated models do a bit better. So there's only a reason for that. I have no time to talk about. And then we have emotions, right? So beyond positive and negative tones, maybe we can look at emotions. So there are some emotion scores, like 27 emotions, and we can also build portfolios based on emotion score instead of positive and negative. And the results also make sense to us. So more excited news give you higher Sharpe ratios. In terms of global market results, I have really no time. I'm just going to show you one figure. So in this figure, the x-axis is number of stocks available for trading. The y-axis is the Sharpe ratio. So apparently, the performance really hinges on how many stocks are available for us to trade. And for US, you get the best results. And for some other countries, you just don't have enough stocks to trade. But the bottom line is large language models, again, do better than system and other back of words approach. So one thing I really like about large language models is this very transparent. Text analysis is very transparent, and you know whether you get a good fit or not by looking at positive and negative words. My last slide is really dig into the differences between large language models and simple word-based approach. So here we're looking at articles in two groups. One group, there is no negation words. One group with the negation words. So with the negation words, if you use OPT, you get 3.86 Sharpe ratio, which is higher than 3.67. And as you can see, mainly the results come from the short side. Short side does much better than the other case. The same thing is true for Roberta, 3.8 versus 3.44, Roberta versus 2.95, right? So clearly, if you trade negative articles, you have a higher Sharpe ratio. But this is not the case for word-based approach, right? For word-based approach, it's exactly the opposite. So this is why, so this suggests us that word-based approach are confused by negation in other more complicated contexts, right? So, and which is why you do worse. All right, to conclude, this is just a starting point to new lines of research into modern text analysis in people. Thank you very much.
Well, thank you so much for having me to discuss the paper. It's a pleasure to be here. So Dacheng has explained the paper very well, so I'll just give you a very short overview and then a few of my comments. So this paper is an application of large language models to predict stock returns. I think it's a very timely application because mostly we just use very simple models to do this, at least in this context. So we usually just count the words, so essentially using the back of words approach. But this paper, well, it just improves upon that quite a lot, and it allows us to use these much more sophisticated ideas. The main thought behind this is that context should matter, right? So if you're just counting words, then what happens is that we're completely removing that context, and some words could be counted as positive, but they could be negated, so they should be negative. So we're just losing all of that context and potentially has implications. So this is what this paper is trying to improve. And it does an amazing job. So I think just the technology that they use, just the amount of models, recent models that they included in this paper, it's really remarkable. As Dacheng mentioned, he showed you this list of the models, really sophisticated. So yeah, so the key ingredients, I think there are two. So first are the models themselves. So they use really state-of-the-art, really these most complicated models with billions of parameters. And that's amazing. And the second one, I think it's actually the data. I really like that data. So they have data on all the news and all the news wires, and then global data, right? So they have it for different countries. And you saw a little bit of in the Cheng's presentation, and there is much more in the paper. So it's the combination of these two ingredients that I think that makes this an excellent paper and really just pushes the frontier on applications of language and text essentially to asset pricing. So the key findings are, well, they do find a lot of improvements in terms of performance. If they create trading strategies, they find higher Sharpe ratios. They also do a lot of additional analysis, which I think is really cool. And again, the Cheng mentioned some of it. So for example, they show that if there are some negations, then simple approaches are extremely susceptible to making errors. And in that context, using LLMs really, really helps. They talk about information dissemination and the speed. So for example, they find that news wires usually work better than articles, probably because they have more time. So there's a lot of suggestive evidence like this. But overall, I think it's a fantastic paper, fantastic data, and it's a major effort, and again, which is different here quite a lot. So just to give you a short overview of the approach. So the idea here is that, okay, we're going to take these LLMs, and we're not really going to innovate on the LLM front because, well, these have extremely sophisticated models, right? And there are people who know how to do it better, computer scientists, and they have the technology and the resources to estimate these models with billions of parameters. But then we're going to take these models as an input to our essentially financial application, right? So what is the output of these models? Well, this is, well, the fitted model, so obviously all the parameters, but what you can do is use this model to essentially produce embeddings for every word or every token in your article, right? And those are really high dimensional embeddings. So basically for every word, you have this vector that potentially has like 2,000, 2,500 dimensions. And that's for every word in an article, right? And that embedding encodes information about what this word is, as well as where it's positioned in the sentence, where it's positioned in the article. So all that contextual information about the meaning of this word within this article is essentially encoded in these embeddings. So they have a lot of these embeddings for every token, so every word in the article, and then they take the average of them. And they say like, well, this is the sort of like what this article is about. So again, this average is still a highly dimensional object. So we're still talking about potential like 2,000 dimensional objects, so 2,000 numbers. Okay. So that would be the input to our econometric model. And they have two applications. So one is the sentiment analysis approach, and the other one is essentially return predictability. So they will use that to predict stock returns and show you the Sharpe ratios, and overall, yes, they find they compare performance to other approaches, and they show that there is a lot of benefit to use this. So I only have two comments. So quite simple. So when the first one is on essentially taking these embeddings, and remember we have embeddings for every word in the article, right? So now you're taking the average of these embeddings. So what they do is very simple, just literally take the average, and that's what this article is about. And I kind of get it, sort of like in this high dimensional space, this is the average word that kind of points us towards what this article really talks about. But at the same time, I think it's a massive dimensionality reduction. And it's not, I'm not an expert in this, but it seems to me that there potentially could be better approaches. And I don't know if the authors want to take these better approaches simply because better approaches might require way more computations, and maybe they will make things less transparent. But ideally, like the way I thought about it, the way you would want to do it, if you had infinite computing power and people to work on this, you'll probably have like a separate decoder or something in this network that would make our econometric objective part of the overall objective of the fitting model, right? Because right now we are essentially having this model that is fitted in a way that allows us to predict something like the next best word or some missing words in the sentence. But it's really not targeted. So these embeddings, they're not really targeted at predicting like the economic things that we want to predict. So I think making it a part of the objective obviously would be better, but in some sense that would also require you to fully re-estimate the model, and that's basically becomes infeasible. So I don't necessarily suggest you do that, but I think ultimately, if companies like Google start thinking about data and how to use this data, so textual data and how to use it to link it to fundamental data, I think there should be like some part of the objective that looks at that. So one similar thing here is the CLS token that some of these models use. They have this special token in the beginning of every sentence that sort of summarizes that sentence. But that token is not really the average of all the words in a sentence. It's a endogenous token that gets fitted by the model so that the model knows that, okay, this sentence might follow this sentence and not that sentence. So again, it becomes the part of the objective. So I think having these things being the part of the objective could potentially lead to even better improvements. And I don't know, maybe some simpler things, like, for example, people in LLM, like, well, we know that LLM can summarize text, right? So we can take this big article and write a short summary or even a headline. So there are ways to potentially, I don't know exactly how it works, but there are ways to reduce that dimensionality to maybe a few topics within the article. And maybe it's better, maybe it's not, I don't know, just taking the action. Maybe some simpler approaches, even like topic modeling on top of this, or like something PCA on this. I don't know if that actually would work, but there's some thoughts on that. Okay, so that's comment number one. And comment number two, well, so basically we have this extremely sophisticated language models in this paper. So this is where this paper really innovates. But on the financial front, it uses like the most old school thing possible, really. It just says like, well, let's predict expected returns and let's create Fama French sorted portfolios on one signal. And again, I kind of get it. I think that's exactly what the paper wants to do in some sense, because they don't want to innovate in multiple fronts. They just want to say like, look, this is what happens if you use the most sophisticated LLM and the most basic finance technology. But I think using the most basic finance technology here is sort of, might be a little bit of a problem in the sense that what do we actually learn economically from this paper? Well, yes, we see some predictions, we see some higher performance of some of these portfolios, but we don't really know whether this is related to all of these other anomalies we've discovered. We don't really know how much improvement we get in terms of like utility or something like this. So I think adding a little bit more on the financial side to this paper would actually be quite beneficial, even if it's a somewhat standard model. So for example, even like Brian's IPCA paper, I think would be fantastic to have it embedded into that framework, because first of all, we probably could do some statistical inference on that. Right now, the paper really is just very descriptive. There are essentially no t-stats, nothing. So it's difficult to interpret what's going on. But also economically, the way I think about this approach, well, they look at these individual stocks and they basically find that this sentiment measure helps to predict these individual stocks. So is it really about systematic risk, or is it about something like alpha? So for example, I think in this IQPAM model, it would be useful to use this approach to say that maybe it's useful, maybe it's helpful in predicting that alpha, the residual, and maybe we can have actually somewhat related, similar model to predict systematic risk. Maybe it will aggregate news for the entire economy, for example. So anyway, so I think having a little bit more sophisticated economic models would really be helpful in pushing both the economic and statistical message of this paper. So overall, I'm out of time. Fantastic paper. I think it's important to use more sophisticated technology in asset pricing. It uses fantastic data, and I just touched on a few basic things where I think it could be improved. But overall, I think it's still an amazing paper the way it is. So I don't know if the authors will be using this, but that's just my take.